welcome to our May event, Come Together, How Fusion Could Change the World. My name is Shinran, and thank you all for joining us again. And I'm super excited about our awesome experts with us to discuss about the potential for nuclear fusion and how scientists from different backgrounds at the UK Atomic Energy Authority and elsewhere are working together to make it viable as a clean source of energy. So without any further ado from me, I'm going to hand over to Tom, the co-founder of Scio, to introduce today's event. Over to you, Tom.
You're going to hear about nuclear fusion, the role that it could play in providing us with clean energy and ultimately help us fight the climate crisis. Now, we were hoping to have three experts from the UK Atomic Energy Authority tonight, but I think, unfortunately, a couple of them can't make it. But what we do have is machine learning expert Lorenzo Zanisi, who is going to be able to tell us about the cool stuff that they're doing, give you a better idea of what's going on in fusion and how the technology can ultimately all help us out. Please don't be shy about asking questions. We've already got a couple in, which is fantastic. We really want this to be as interactive as we can. The more questions you ask, the more you'll get out of this. If you want to ask anything, please send it to us, as some of you already have in the chat function in Zoom. If you're viewing live on Facebook, then you can type your question in the comment box and we'll pass it on to Lorenzo. I should say, if there are any questions that we're not able to answer just now tonight, we are going to do our best to record a couple of extra things or put some material out to get those answered. So if we can't get to them now, I'm really sorry about that, but we will make sure that we get stuff to you as we should. I'll just say a couple of quick words about Scio. We create events and platforms to give you access to scientists and other experts and hopefully inspire some people to pursue careers in science, technology, engineering and maths. As you've probably gathered by now, we're recording today's session. We're going to make it available on YouTube. If you want to watch it again, our account name is Scio, that's SCIOORG. It'd be really great if you could subscribe while you're there. It really, really helps us, and it means we can easily keep you updated with future events. If you enjoyed the panel today, please do share the recording with your friends. I've really rattled through my usual intro there. That is all from me for now. Lorenzo, over to you.
Hello. Thank you, Tom. Thank you, Shin. Thank you, Sophie. Thank you, everybody, for inviting me today to speak about nuclear fusion and what nuclear fusion can do for our society and how AI can help specifically. So I will first quickly, well, obviously share my screen, I guess. Yep. And go in presentation mode. And hopefully that works. There we go. So we are UKIA, we are the UK Atomic Energy Authority, and we are working towards achieving nuclear fusion, which, as I hope to convince you in the next few slides, this is the ultimate energy source for us and for our world. Well, so first of all, why do we need fusion energy? Well, this is quite easily said. We know that we are in an energy crisis. We know that we can't rely on fossil fuels any longer. Fossil fuels are very polluting and they are bad for our environment. We will never be able to, keep living on this planet if we keep using fossil fuels. And there is a significant push from the public, people like you, towards moving away from this, and you have all the right to demonstrate about this. So the other problem with other sources of energy is that they are not as reliable. For example, if you take wind, the wind doesn't always blow. If you take solar power, well, the sun doesn't always shine. And I mean, as an Italian, I can tell you in the UK, that's definitely something that I see a lot. But from the sun, we can do something else. From the sun, we can get inspired and do fusion. So I'm an astrophysicist by training. I studied galaxies. Galaxies are made of stars, and being involved in another field, such as in a somewhat different field, such as fusion, is incredibly inspiring because it goes from, like, there's a seeing the energy of the stars powering galaxies, and then seeing the energy of the stars on the Earth is incredible. So what is actually fusion? Well, fusion is a process by which you convert two light nuclei into a heavy one. And when that conversion happens, some mass is lost, but it's not actually lost. That mass is converted into energy. And that involves the famous formula by Einstein, E equals mc squared. So the kind of fusion energy that we get is really a lot of energy, but we have a lot of problems in trying to harvest that energy. So how do we do this on Earth? We use different kinds of machines, and these are called the particular machines that we use at the UK Atomic Energy Authority are called tokamaks. We have two tokamaks. One is called JET, that has been in the news recently, and one is called MAST, that has also been in the news last year and has gone a major upgrade. And so what is a tokamak? A tokamak is a kind of donut-shaped machine where plasma, that is a state of matter where essentially it's a gas that is ionized. What that means, it means that the positive nuclei and the negative electrons are not bonded together anymore. So an ionized plasma responds to magnetic fields. So you can make this plasma essentially levitate, a bit like a ghost in your machine. And well, in that way you try to contain this plasma and hope essentially that the interaction between the nuclei will give you fusion. And that is indeed what happened. Like, we do see fusion. What we do need to do is to scale this up to make it a reliable energy source in the future that can substitute hydrocarbon sources. So, as I said, in the UK we have JET, which is the machine that you see here on the top right, and then we have MAST upgrade in the bottom left, and then we have also another machine that is only in our minds so far, which is called STEP, and I will tell you about STEP in a later slide. So, what is UKIA? So UKIA, we live near Oxford. We live in Culham. Culham is a very small village, and UKIA was built in the 1960s. The Culham, the site at Culham, and since then we have grown a lot. We have a lot of facilities that can help us tackle all the different problems of fusion that I will tell you later on. So we have, of course, our two machines, MAST and JET, and then we have an entire facility to try to figure out which are the best materials to put in our tokamak. The problem with materials is that they get irradiated, and they need to be able to withstand a lot of irradiation from neutrons, which breaks them, and a lot of heat, which melts them. So we need to figure out what are the best materials that help us avoid this thing, because if that happens, of course, our machine will not run anymore, and it's very expensive to build a new one. Then we have, of course, our manufacturing facilities, and we have our robotics facility, because, of course, you can't go, you can't go inside a fusion reactor with your hands, because especially after a campaign is over, the environment is still dangerous. And I should say inside the machine. Outside the machine, nothing happens, nothing transpires. So we need robots to go in there and take care of all the handling those materials for us. Also, machines are quite small for human standards, so you don't want exactly to climb inside your machine like Godzilla or something. You risk also damaging it, so you need something very very lightweight in there. And yeah, so we are actually always expanding. In the past year only, we have expanded from 1,400 people to over 2,000 people. And the department that I am in, advanced computing, which you will hear more in the next sets of slides, has grown from 12 from 5 years ago to over 50 this year. So this is an incredible growth curve, and we are on our way to delivering fusion. And I should also say that the UK is one of the best places in the world for fusion. As I said, we started in the 1960s with fusion research, and there is so much legacy knowledge, and so many people are still with us that have witnessed the very early start of this exciting field. So this was a quick introduction to who we are and what we do, and I will move to a different set of slides to talk to you about what I do specifically and why I'm excited about it. So I will reshare my screen, and there we go. Hopefully this is okay. So in this other set of slides, I will tell you why artificial intelligence, I will try to convince you, in fact, why artificial intelligence might be critical to achieve fusion power. But first, I will obviously introduce myself, which I haven't done yet. So I am Lorenzo, I'm a data scientist at UKIA. I was born and bred in Rome, in Italy, as you can probably tell from my accent. I did my master's in physics and astronomy at the Sapienza University. And then 5 years ago, I came to the UK to study my PhD in astrophysics, where I was studying galaxies smashing against each other. In my free time, when I'm not a scientist, I love to do several things, and I love baking. I love doing outdoors activities, and incidentally, I also play the clarinet. Just a quick recap about why fusion is brilliant. So fusion is carbon-free. Fusion is incredibly compact as an energy source. Consider that 1 kilogram of fusion power is worth as much as 10 million kilograms of hydrocarbon, of an hydrocarbon like coal, for example. But there is no carbon emission from this fuel, and in fact, you need as much as just 1 bathtub of water per person for an entire lifetime. Can you imagine if we manage to exploit that source of energy? That would be fantastic. The waste, people are sometimes concerned with the nuclear waste, but which is proper of fission power, which is a different kind of nuclear power and not the kind that we try to achieve. The waste that comes from nuclear fusion is manageable, and it's very low. And our is basically unlimited fuel because, well, it's water, so we have the sea, and it can provide a reliable baseload, as I said. I should also say, like, this slide adds something more to what I said before about why is always important. Why is important to to try to achieve fusion. And apart from, of course, the outcry, the public outcry, because hydrocarbons are not viable, we have also a war situation that has exposed our over-reliance on fossil fuels. But also we have an incredibly good landscape for the private sector, where billions of dollars are being invested in startups. So this is a sector that is definitely growing very, very fast, as you can see from this graph. And so, as I said, the UK has 2 tokamaks at this moment, which are MAST and JET, but also the UK wants to be at the forefront of fusion energy. And it wants to do so by building the first ever working fusion power plant called STEP. STEP will deliver 500 megawatts of energy. That is a decently sized coal power plant. And it will do that in a clean and reliable way. And actually STEP is being, the site where STEP will be built is currently being chosen. And there are, I think, five sites across the UK where this could be. And maybe will be somewhere near where you live. The UK government is so serious about fusion energy that we even have a strategy for fusion energy, which is something that only the US has in the world. I will skip this couple of slides. So, but I want to cut to the chase and go a bit more into the more technical details about what is this thing about, you know, combining fusion and artificial intelligence. Well, the first two things are, of course, that, well, fusion is really cool because, I mean, look at this picture. This is a picture of MAST, one of our tokamaks, and these are plasma filaments. It is so beautiful, and you know, working in this is just crazy. At the same time, artificial intelligence is also an incredibly cool field that only in a few years has revolutionized completely our world. In your smartphone, probably your camera post-processes your pictures, your photos with AI. Your Instagram feeds decides whether you like cats or dogs more with AI. But I think that there is a better use of AI than deciding whether you should watch videos of cats or dogs, and is, you know, to make fusion happen. So so essentially we have here an incredibly cool case. We have cool science to do. We have a cool methodology, and we have an incredibly compelling objective. And that's what makes me personally so excited about nuclear fusion. So I've talked about AI, but what is exactly AI? So according to this guy here, who was known as the father of AI, AI is some kind of machine, in a way, that can learn from experience. So interacts with the world and learns from its own experience, which is kind of the way that we humans learn. And the way that this machine would learn is that it would alter its own instructions to keep learning. What it means is that the machines goes out in the world, it receives data. These data, you know, triggers some kind of internal mechanism in the machine, so that the next time, you know, in a similar situation, the machine will know what to do. What does it mean in practice? So in practice, we've got an algorithm. An algorithm is some kind of, you know, computer program that is fed with some data that comes from the real world. And this algorithm understands complex patterns. And let me clarify that in no way understands complex patterns in a way that we can do, because we have this multitasking ability that AI is not quite there yet to achieve. And but the good thing is that computers are faster than humans, because, well, electronics, I guess, works better than biological neurons. And so so AI is faster at doing at doing these things than humans are. And so why do we need this tool in Fusion? Well, first of all, because we've got lots of data, as I will show in a moment. And then because Fusion is a very, very hard challenge. We've got so many challenges on so many different fronts. We need help from, you know, highly specialized, high throughput, high data machines. And we need fusion energy now. So it's good that, you know, it's good that AI is faster than humans. So when I say lots of data, what does it mean? Well, this is a bit blurry, but you will forgive me. This is an image of a tokamak from the outside. And all those arrows pointing inwards are diagnostics. These are instruments that can tell us about the state of our machine, the state of our plasma. And in a future tokamak, this will be about 1 to 2 petabytes per day, which is like streaming Spotify for more than 1,000 years, but condensed in only one day. So the amount of data that we get is really huge. Secondly, we need to operate our tokamak. And all these devices help us understand what our plasma is doing inside the tokamak. So we need to hit our plasma. So the way we start a machine, we bombard it with some microwaves, and we bombard them with some radiation, and we make fusion start. But that needs to be controlled. You can't do it, in the way that you want. It won't work in just because you touch the plasma, something happens. Then we need to know how our plasma is moving inside of our machine. So we need to know where our plasma is, and we need to see whether our magnetic fields are, and we need to know. We need to see where the disruptions are, because plasma can undergo disruption. So here you can see that these filaments that I showed you earlier actually are not static, but they bubble up. And like when you have a pot of boiling water, and the water tries to escape, that's the same thing that plasma tries to do, which is obviously not good, because if the plasma undergoes a disruption, this very hot stuff goes on the wall and destroys our machine. And then we of course need to monitor our machine and see whether there's anything that is wrong inside of it, like literally structurally. The other problem that we have is that we need to plan our experimental campaigns, and we need to plan how our machine will operate in practice. So we have this. We need to do this with simulations. There's no other way. This is an engineering problem. The problem is that these simulations are incredibly expensive. For example, what you see here is a simulation of a magnetodynamical instability, and this is 14 milliseconds, really slowed down version of what happens in real life. But it took 2 months on a supercomputer for a single machine. Now imagine that this is a problem that we have for a lot of different modeling. So we need to model different things in our plasma, in our machine, and each of those simulations takes that long. And every small change in machine design will have an effect on how our plasma behaves. So we need to rerun our simulations, and this takes a year or even more. This is clearly impossible. And if we want fusion energy now, we need to build surrogate models. So that is models that are not exactly physical, but imitate physical models, and that can replace these expensive simulations. So when we put this all together, we have what is called a digital twin. So a digital twin is a concept in engineering that is becoming really hot. And so if any of you in the audience will go for an engineering degree, or is already an engineer, maybe will be interested in this. So here on the left, we've got the real tokamak. And as you can see, it's not particularly pretty. Well, not to me, because I'm a theorist by nature, but you see it's all wires and buttons and all that. And on the right-hand side, instead, we have a digital copy of our machine. This is a digital copy that gets data from the machine, and there is a system that embeds this data in our simulation, in our digital copy. Inside this digital copy, we know then what is the state of our machine and our plasma in the real world. But we can run simulations or emulations, imitation of the real world, to see where this machine will be in the future, and then we can act on what kind of response we should have, and all of this can be powered by AI, as I'm going to show you in a second. So, for example, this was some research from Google that came out only a couple of months ago, and here basically what they did was they used an AI that managed to control the shape of the plasma. So here you see different blobs moving in different ways. The video is a bit short, but hopefully you can see that the plasma moves around and then it stabilizes because, well, our machine, our AI, given some instructions, is putting the plasma there and it's making it stay there, and so the plasma is not moving around. This is another instance. So here on the top, you can see images from a camera that is inside the tokamak, and from at the left you see this is the start of the operations, and on the right is the end of the operations. And on the bottom is a prediction done with machine learning, with AI. So you can see that there is an incredible similarity given the, well, an incredible similarity, they're basically the same image, given the initial conditions, they get to the same final stage. So we can forecast what will happen to the plasma in real time. And we can also accelerate our models with artificial intelligence. For example, in this work, these people have taken a complex simulation that took 5 hours to run and have reduced it to only 1 minute. And you can understand that with this, you can explore your regime of operations a lot faster. So we obviously this is extremely promising research, but it's still not quite there. It's enough to show that AI has a lot of potential for fusion. But on the other side, we have only about 20 people in the UK working in fusion. This obviously needs to be scaled up. The UK, as I said, wants to make STEP. As I shown before, STEP is already looking for a home. So, but AI has so much to give to the planning of STEP. Luckily, the UK is also an AI superpower. So we need to fuse these two things a lot better, and to leverage our knowledge of AI that we have in the UK with our knowledge of fusion, and deliver fusion energy. We can do this. So hopefully I've managed to convince you today that fusion is coming, is something that is really close. As somebody said earlier in the start of this webinar, I would say, fusion is always 30 years away. Well, this time actually we are there, and AI is going to help us. So I hope you enjoyed this, and thanks for your attention.
Thank you very much, Lorenzo. I think we've actually, I think we have Julita here, I hope.
Awesome.
Yes, I am here.
Brilliant. Over to you, Lisa. Thanks for making it. Well, I'll hand over to you as time is relatively short.
So, okay. Going to share. I think it's this. Can you all see my screen?
All good.
Thank you. Thank you for organizing this event. My name is Julita Inca. I come from Peru. I have been working with UKAA since 2020 during the lockdown. So I am part of the challenge, digital challenge, to be able to do the simulations of a digital tokamak. I want to do a very brief timeline of a tokamak because it's around 100 years of work for that thousands of people or millions of people have been done. And I also want to point out what are the efforts that other people have done in digitalization these tokamaks. And I also share with you what I'm doing in favor of the digitalization. So I'm gonna start with a timeline about nuclear fusion. Well, the concept has been conceived since 1920. Fusion is a energy source. Who was the inventor of this? It's being a group of physicists, and the first I am very glad to find out some information about the work have done also for women in the past. And I was very focusing in the tokamak itself, so I think I can mention in 1950. At that time, very long time, it was it has been achieved the magnetic confinement fusion. So what I want to say, I was like searching about is because there are many tokamaks in the world. They were trying to do the best design, optimization of these designs. So I was curious, how was the first one? And well, Russia with the T1, they were one of the first in the world. Like if you can see in the image, how it's different the shape. Like we had at the time in comparison what we, well, not we, people or scientists, um, or the effort of many countries, because it's included USA, UK, Japan, and several countries in Europe. They were contributing to make it like the joint European Taurus. So it is in France. No, I'm sorry, it is JET, the project called JET. And in the 1918, 92 specifically, they were discovering like the H mode, uh, rather to, well, when we are talking about tokamak, we are not just talking about infrastructure, we are also talking about the plasma itself, how to do the simulations, or how to make it work, and also the surface. If this plasma contains a lot of heat, it might damage the surfaces of the tokamak. So there's a lot of effort in studying the materials of the tokamaks, um, and the interaction of the whole system. So in 1983, after 10 years, it was achieved plasma in the tokamak. And why they are taking so long? Why it's several years? It's the effort is, it is known that it is possible to make the fusion in the earth, but make it confine it and make it holding like for longer, it that's the challenge. So they were doing so many efforts. They have put a lot of energy sources or ions and machines, but the outcome was like a very little. So including this year, well, I am skipping what of the most what I am here. I mean, a step is a project, which is the spherical tokamak for enterprises. I am part of a step. So what they are pretending is in 20 years, less than 20 years, they want to commercialize fusion. So we want it for everyone and reachable for everyone. So I was telling you about all the efforts of several years, and these, including these years in February, many scientists on UKAA made it possible for some seconds. So we are still in the way of doing what. That's why we need more people, more scientists, because it's the whole system that that has to orchestrate to make it like work for at least 10 seconds in one more year. I really cannot say dates or numbers, but the challenge has been for a century. What has happened in lockdown? I was checking online, like it was like really close. So why Lorenzo was telling us about machine learning or AI, even including the Forbes site, has been done some research. If it is, if we are even close, how close we are, if we are applying the machine learning or AI, it will help us to make it. Um, then UK also wants to build. Everyone wants to be the first in make it. From now, we have the plan of 20 years. I am also set in my mind, in my effort, all my effort day and night. Okay, I have 1 year less every time, but I am not the only one. This is the work of physicists, mathematicians, people in computing. So um, we need more backgrounds involved, like maybe also people who are doing simulations at nanoscales or simulations with particles, OpenMC, Monte Carlo. We have several theory behind this phenomena. I can say a phenomena. So I am setting or I'm sharing with you some links so you can have a look of how what is going on right now, because maybe I can tell this like the errors from the past. We need to do new things to overcome the problems we had over a century. So I think the application of machine learning or HPC resources might help, but it's not only the application of technology. We have to check what is in behind that, what is the math and the physics behind it. Well, I am also sharing what UKAA is studying, what are the researchers done, what are the optimizations of the components of the tokamak, what are the multiphysics involved. So I think this is public, so you can have a look as well. In the regards of the digitalization, you can see here the tokamak has several components, and it include for now it took me a year to understand in the basic this is the cassette of the monoblock diverter. So I think I will show you in detail in one more slide. So
Sorry, Helita, I think we're a little bit short of time. Sorry to cut you off, but I think we just need to save a little bit of time for questions and
okay,
answers. But
I
I think,
can just 1 more minute if it's okay.
yeah, if it's 1 more minute, sure.
Yeah. So sorry. This is what I'm doing with my contribution about the diverter monoblock. All of this is the tokamak. This is the cassette in the basement, and these are around 92 cassettes. But I am only focusing in this small square here. So I am using Moose. This is a software, a framework that use multiphysics, and it already has developed some kernels to use to do the simulation of the temperature or the displacement of the material. So I set up, and my work specifically is not only doing the simulations by using the configuration that physics or mathematician has done, it's using MPI and using the cluster. So I can speed up the simulations, and instead of taking 2 hours, I can make it into 2 minutes. So what I am also doing is launching some jobs and doing benchmarking using Bash, scripting, and Python. Sorry for taking your time so long. And you can find me on Twitter. I have a master in the University of Edinburgh. So I thank you again for listening.
Thanks, Helita. Please do stick around, just as we have a few questions coming in. I'm going to ask this to both you and Lorenzo. What is so this is from Roger, who's asking, what's the best guesstimate of how long before fusion generated electricity is on the grid? When does this start becoming real?
Well, I think I told you, like, it is already proved that it's possible to make a fusion. So the achievement is the challenge now is to confine it longer for a longer time, because it is the ions are positive, they repelled. Am I here?
You're here,
So
don't worry, we got you.
yeah, so heating up and make it keep it long, stick together, but longer time. That's the challenge. I don't know if I'm answering questions, Lorenzo. You want to say something?
Yeah, so basically the idea is to have STEP, this machine that will put energy in the grid in the 2040s. And there are other companies around the world that are trying to do the same thing. So we're all competing with each other with this. But the 2040s is a realistic timeline, and hopefully when that works, we will have a massive scale up, and by the end of the 2040s and start of the 2050s, we will have fusion power as our baseload, and humanity will be powered by fusion largely. That's the idea.
Cool. We have a question here from Matthew, and he says that he enjoyed seeing some, he says, jaw-dropping video from inside a tokamak recently, and he's asking how can any kind of video equipment withstand the pressure in there. Hi, Bella. We will get you involved as well. Yeah, sorry. Does anyone want to understand that? Can any video equipment actually withstand the inside of a tokamak when it's firing off?
Oh, maybe Bella, do you want to take that? Or maybe I can answer the question. Can you re-summarize a bit? Sorry, one second. Can you summarize the question again, Tom?
Yeah, we have someone here who's enjoyed seeing some video footage from inside a tokamak, where I'm assuming is actually going off. How can anything actually withstand what's going on inside a fusion reactor?
Yeah, this is part of why fusion energy is a materials challenge. So we need to have materials that can withstand those kind of heat loads. And but what we do is that we try to have like a sort of configuration where there is some kind of plasma blanket, around the main core of the plasma, and then there are two kind of legs, you can call them, that go in the. If I may share my screen again, if you don't mind, so I can show one slide on that. There we go. So yeah, so you see in this portion here on the bottom and on the top, this is what is called the diverter. What Julita was talking about, and this is where all the heat is funneled. But along the diverter, along that magnetic field, there is something that happens for which, well, we need to engineer, of course, your system for that. But essentially, we can make an incredibly strong dissipation of heat along there just with radiation. So the plasma just loses all the heat by radiating it away with light. So we convert heat to light essentially, and in this way we can avoid burning the walls of our machine. But of course, if we have a big disruption like the one I was showing in a video, that will go on the walls of our machine. 100 million degrees on the walls will just melt it. So there's no way around it. We need to not have those disruptions. I don't know if Julita or Bella want to add anything to that. Okay, cool.
Well, actually, that kind of leads me to one of the questions I had, which is, how, compared to nuclear fission, how safe is a tokamak reactor? Let's say the worst thing happens, something goes really, really wrong. What's the absolute worst thing that can happen here? You just talked about something hitting the wall of the reactor that's at however many million degrees. That doesn't sound good, right?
No. Bella, you want to take that?
Yes, I'd just like to say I'm sorry, I had a mix up with time, so I really apologize for not being able to be here earlier. That's on me. Do apologize for that, but I can definitely answer this question. So I'm Bella Boulderstone. I'm the Public Outreach and Engagement Officer at UKAEA. And a lot of my time is spent reassuring people on the safety of fusion, because I am sure that Lorenzo and Julita told you sort of just how difficult it is to get this thing going. And we actually only have 5 grams of fuel in the machine at any one given time. So it's not actually all that much. So if it were to have a catastrophic error, what would likely happen is that the heat would be dissipated into the machine, probably break the machine, but there's no chance of a runaway reaction. As soon as we stop heating the reaction, it stops. Plasma doesn't want to be a plasma. Plasma would prefer not to be contained. What it would really like to do is become a much less high energy gas. So there's unbelievably no chance of this continuing on, as we don't have all of the natural advantages that the sun does in getting fusion to do its thing.
Cool. I was just going to say, sorry, I meant to say this at the start of the Q&A. I think we're going to probably aim to wrap up about 5 or 10 minutes past, if the participants can still stick around. Sorry for the delay, everyone. If I move on to the next question from Radek, who asks, how reliable or accurate is the state-of-the-art numerical modeling of the fusion process? Lorenzo, Julita, this sounds like it's probably one for one of you two.
Maybe that one is more for Julita than for me, that is actually involved in this a bit more.
We have in regards to the simulations, or we are basing in the governing equations, which are approximations. Computationally, you cannot have an exact numeric result like when you are doing analogical or analytics calculations. Even MATLAB or COMSOL, any framework or multiphysics framework you are using, in the behind you have only approximations. And what I am studying now is how to make it accuracy, how to make it repeatable, because as I mentioned as well, is orchestrating many parameters. You have to combine the boundary conditions, you have to consider the geometry, how do you mesh, what are the element type of the meshing methods. So I think in any part of the world, I am aware about what's going on in USA. They are doing only approximations, and the accuracy or the validation of my results is based on benchmarking and make it repeatable, so everyone else can do a validation or a confirmation of my results. It's okay.
Yeah, actually, this actually takes us, just from something you mentioned, Lita, this takes us to one of the other questions we've got in from Susanna and Jorge, who ask how many tokamaks or similar devices there are around the world, and in what countries. Yeah, I guess, who are you competing against? That's the right word.
Yeah, I think if I can take this one, I think there are about 200 tokamaks. I don't know if they're all operational or if this is just a number of all the tokamaks that have been built so far, and some of them have been decommissioned. But yeah, there are tokamaks in Africa. There are tokamaks in Europe, in the US, in Brazil, in India, in China, in Korea, in Japan. All the world is littered with tokamaks, essentially. So that's roughly the number, 200, 250. Yeah, I don't know all of them. So
I think now in the UK, in DeepCode, you have a smallest.
Yeah, they have. There is this startup called Tokamak Energy in DeepCode. They have their own tokamak, for example. And there is another startup that's actually is backed by Jeff Bezos of Amazon, that came to Callum, but they're doing a completely different kind of fusion. They're not using tokamaks. They're using a different kind of machine that I don't quite understand yet. Yeah, there are also other kinds of machines around the world. It's not only tokamaks. You can try to do fusion in different ways.
So actually, another bit of that question was what countries are any other reactors in? If there's 200, then I'm not going to ask you to answer that. Alan asks, so in fusion, the energy that's released is kinetic energy. How is that kinetic energy converted into electromagnetic energy? And also, and this is where it gets slightly more too technical for me, also is the spectrum of the EM energy dependent on the atoms that are being fused? There's a couple of bits to that question. Who'd like to have a crack at that?
Sorry, could you repeat the last bit of the question?
Yeah, is the spectrum of the EM energy dependent on the atoms that are being fused?
Oh yeah, that's a great question. I can totally get this if Lorenzo and Lisa don't want to. So so the energy that's released is so we have our deuterium and tritium. That was me mangling deuterium and tritium together to make one new thing, a fusion, if you will. We push those together, we come out with a helium and a helium atom and a neutron. And because of the conservation of momentum, we get a slow helium atom and a quick neutron. And that's where the majority of the energy that we're interested in is. And this fast neutron, we're aiming to capture it in future tokamak designs through a lithium blanket. The lithium blanket will act as a heat exchanger with water. So what we'll do is hopefully pump liquid lithium through water in pipes, and that can heat up water, turn it into steam, drive a turbine, go onto generate electricity, go onto a step-up generator, national grid, etc. And that's just the way it's always been done in terms of power plant designs. And that's what we're aiming to do in the future. So we're aiming to capture the fast neutron in lithium. And the reason why we're doing lithium specifically is because that can also make tritium. So we can keep making our fuels, because deuterium is pretty common. Tritium is a little bit less common. So we're trying to create our own fuels and become self-sustaining. And the next question of, does the electromagnetic radiation depend on the fuels that you use? The inside of our tokamaks is a beautiful pinky purple color from our fusion plasma, which is really gorgeous. And that is because of the deuterium and the tritium that we use. For our 100,000th pulse, we actually ran a helium. Yeah, we turned the machine on using helium and helium. And that was actually a beautiful blue color. So it absolutely does depend on the fuels that we put into our machine.
Brilliant. And I have a super technical question that I've just been stripping down a little bit so that I can read it out a little bit easier. AC asks, right, deep breath. Muon catalyzed fusion allows nuclear fusion to take place at temperatures significantly lower than the temperatures required for thermonuclear fusion, even at room temperature or lower, right? Not my words, those of AC. It's one of the few known ways of catalyzing nuclear fusion reactions, and they ask, can someone please explain how that works? Sally, you look enthusiastic. I'm glad, because I'm not sure I understand that. Yeah, I guess in terms that even I, non-scientists, could understand.
I think my first question is going to have to be pleading ignorance, unless Lorenzo or Lita know anything more. I think I was reading something about muon catalyzed fusion in trying to push together both fusion and fission. So using excess neutrons from a fission reactor as a way to continue on a fusion quest, I suppose. But other than that, I'm afraid I don't really know that much about it. And I don't know if Lorenzo or Julita do. So I'm going to plead ignorance on that one.
I have no idea. I don't know. I would need to read up about it to get a you know, to get an opinion on this. I don't really understand this. I mean, it's not understand. It's the first time I hear, so it's you always learn, I guess. So yeah, I don't know if Lita maybe has heard about this before. No, okay.
Sounding sounds like maybe this isn't the right panel. We will AC try and get an answer for you though. That's definitely interesting. Well, that's definitely complex enough that we might need a little minute to think about it. We actually have someone saying that they're typing us an answer from the audience, which is great. We'll get that to you if we've got time. We are going to have to wrap up in a couple of minutes, but I just have one last question, which is probably best for Lorenzo. Catherine asks, how are researchers ensuring machine learning algorithms don't oversimplify simulations and don't take into account important interactions in their effort to reduce computing time? I guess that probably says do take interactions into account rather than don't. But yeah, how are you making sure that those algorithms don't oversimplify things?
That's an excellent question. It's an absolutely fantastic question, and this is the reason why AI is great, but we need to be careful. We don't need to treat it, you know, as an oracle, because it isn't. AI is only as good as the data is trained on. So this is something that is very, very important to keep in mind. AI can give us a sense of how uncertain it is for a given prediction, and this is what we hope to exploit. For example, if it was trained in a particular set of configurations, to deal with a particular set of configurations, maybe it's going to be able to generalize well to other configurations in that are close to where it was trained on. But if you try to do something wildly different, well, first of all, you should ask yourself whether you should even try, because you haven't tried, because you know that your AI doesn't know about it. But if you decide to do it, the AI, there are ways that the AI can tell you, I don't really know the answer here. It can output a very uncertain answer, and then you can say, well, then that's human judgment. You can just say, I'm not really sure I want to trust what the AI is doing here. So there's always needs to be like some kind of checks that you are doing. You're not doing anything that is outside of the regime of applicability. That also works for simulations, by the way, just physics simulations. Some of them have some simplifications because otherwise it would be too expensive to run, and they are validated only on some particular conditions. For example, some simulations that I'm working on are very good for JET, one of our tokamaks, but are not good for MUST, the other tokamak that we have. And we know that, and we don't even attempt to run the simulations for MUST. And I guess that's the same that would need to happen for in AI, if that answers the question.
I think so. I will just read out. So Joseph has left an answer to the muon question. I'm going to read it out so that we've got it on the record here. So it's about the binding energy in the hydrogen. A muon replaces an electron in hydrogen, means that it orbits closer to the nucleus and therefore can get closer to other atoms and fuse before being repelled by the electron repulsion. It's as easy as that. But yeah, no, I'm glad we got that answered. Thank you, Joseph. That's really, really useful. Unfortunately,
so is that all about just reducing the electrostatic repulsive force?
If you say so, Bella, I'm going to assume that's correct. Yeah. Joseph, thank you. And thanks to everyone for attending and speaking today. That is all from me and from the panelists today. Thank you. Sorry that we've overrun a little bit. I'm just going to very briefly hand over to Giulio to play us out.
Hello, everyone. I'm Giulio from Scio. Thanks for bearing with us again. It'll be real quick. I just wanted to thank the amazing panelists for such an interesting conversation. I hope you learn more about fusion and what's the future of this technology. And let's also thank Lauren and Sophie from the public engagement team at STFC. They were helping us behind the scenes to make this event run smoothly. And of course, Thanks to all of you audience for attending this event. At Scio, we want to connect experts to the public. In our recurring events, we heard the words of experts on various topics spanning from Hyperloop to vaccines. If you missed them, you should definitely go watch them on our YouTube channel, where you can also rewatch this event. Don't miss out on future Scio events. We have plenty of ideas for giving you scientific content straight from the scientists' mouths. Subscribe to our channels on social media. Links are in the chat or in the description below. That's all from me. A big, massive thanks to all of you again from myself, Dom and Shinran, and we hope to see you again very soon. Thank you.
Okay, thanks from me as well. Thanks, everyone. Have a good evening.